And we are again here with the next topic at MIDI C++ 2024. Rainer Grimm is presenting an overview on C++ 26, and that is really something to see and watch what we have in the standard, which is coming out after 23. So Rainer, I'm looking forward to your talk. Please take it away.
Thanks a lot, Jens. I'm happy to talk today about 26. Honestly, 26 is not fixed. Meaning, a lot of stuff I'm talking about may change, but this is my own view. I want to talk about the core language, the library, and finally about concurrency. And when you look here carefully, you see already the three big features: reflection, contracts, and finally stood execution. Now let me jump in. First, I talk about the core language. By the way, I show you many examples, but only for the core language, because the library is so far, let me say it differently. There's no compiler available for the library. Therefore, we see a lot of examples for the core language and for concurrency, but not for the library. Let's talk about the maybe biggest feature, reflection. What's reflection? It's the ability of the program to examine, introspect, and modify its structure and behavior. Here's the first extremely straightforward or simple program. This makes no sense, this program, but let's see what's new here. We have here the reflection operator. You'd see two currents. This reflection operator converts the int into the reflection value. So this R here is the reflection value. This is what I can examine. You can also do it in one step. I have to add something. With this reflection operator, you go from the source code to the reflection domain. And with this so-called splicer, you jump back from the reflection domain into the source code domain. And this is essentially only a back and forth algorithm to go from int to reflection int to int back. In my examples, I always use only one car. The reason is this was the original syntax, and all the compiler only support one car. But here I have two of them. This is the new syntax. Let's go further. So far, this was a simple example. When you want to dig deeper, here's the corresponding proposal. It holds true for reflection, contracts, and stood execution. There are only minimal viable products, meaning we can expect more with 29 or further C++ standards. They only have the minimal content to make sense. And reflection supports many meta functions. Meta function sounds a little bit crazy. This means this is just a function which is declared const eval. Meaning with this function can only run at compile time. And all this function except one type. This is the reflection type, meta info. Now let me show you two examples. I don't want to go too deep into the details. They may change. This is from David van der Borde. I make it a little bit bigger. And what this does is something which is often complained about C++. You can display the names of enums. Have a look. I have here enum. This was too much. Damn, hey. Now I do it differently. Now I have it. Oh, this does not work with compile export. Let me do it. Oh, yeah. Here we have it. Here have my enum, you see? It has the enumerators X, Y, E, and Z. And the corresponding values 0, 1, -1, 99. And this is exactly what you see here. I can display them with their name and their value. How does it work? From each, you see it here, one caret, I have my enum. I make a reflection value of it. From each enumerator, I take the name here and its values. And this is, by the way, one of this meta function. And this is all what I do here. And therefore I can display the members of an enum. Get enum data, you see this is const eval. So it runs at compile time. Then I create an array from enum item E and of this size. And here I ask my enum, I reflect on it to get its size. And finally, I put all the enumerations on my result array. Its name, its value. So let me jump to the next example. I can also analyze the structure of a class. This time I let it a bit smaller. I say here types and their sizes. Now I go to type sizes and display for each type its size in byte. And this is what I analyze. I have an array of types, and you see these are reflection values. And then I use this lambda function here to transform the type into its size, because I want to get its size. Transform stores its value at R. Now you can see I can analyze my data type types. This was reflection. By the way, this was not reflection. There are way more examples in the mentioned proposals. Let me jump back. Now I come to contracts. First of all, what is a contract? It specifies interfaces for software components in a precise and checkable way. The software components are functions, methods that must fulfill preconditions, postconditions, and invariants. A precondition is something what must hold up to the entry in a function. A postcondition is something which must hold up the exit from the function. And an assertion is something inside the function which must hold exactly at that point you use it. I said it must hold. All three require a predicate. This means a function which returns a boolean. By the way, this way of programming is sometimes called design by contract, and it goes back to Eiffel, to programming language Eiffel. Here's the first example. I have a function f, which has a precondition I greater than 0 postcondition. This is the return value. L greater than 0. And this is the invariant. Here it's called contract assert. Here the value of I must be at least 0. Let me add a few remarks to it. Pre and post. You can add pre and post condition to a function. You can add an arbitrary number of pre and post conditions to a function. You can even intermingle them. Pre and post are so-called contextual keywords, meaning there are only keywords in this context, but not in the other one. They are only identifier. And they are positions at the end of the function declaration, you see? Here it's the function declaration, here starts the function definition. Post can have a return value, of course. And an identifier must be placed before the predicate, followed by a colon. By this convention, R is the return value. And contract assert, this is a keyword. Otherwise, it could not be distinguished from a function call. So what's happening when I execute this program? Currently, we get a runtime error, you see? I invoke f with -1, but precondition is I should be at least 0. Therefore, I violate the precondition. And this is what the compiler is saying. Contract violation in function f at line 6, and here's the predicate. So, you see, currently, we only get a runtime error. Now I come to a small feature, which I love because I often used it in Python. We have now a placeholder. This is the underscore. Can be as often used as you like. It does not emit a warning when not used. It's frequently used in Python. See, sometimes you get something back for a function you don't need. Therefore, you can just assign it to an underscore. Here you see it. I have a function returning a double, but I only care about the string value. Now I can use 2 times the underscore, which makes it crystal clear. The int value and the double value are not used here. The compiler will also not emit a warning in this case. And I find this is a nice feature because it improves the readability of your code. And what's more, I heavily used it in Python. You know we have static assert in C++11. But now we have 3 different forms. And I in particular talk about 26. With 11, static assert, what's its job? You have a compile type predicate, meaning a function or function-like thing, which returns a boolean at compile time. And you can also provide it in unevaluated string. Meaning when this static assert fails, the unevaluated string is displayed. With 17, you can also use it without this string. But now a little bit changed. Instead of the unevaluated string you can use in 26, I use defined type. This user defined type must have 3 members: size, data, and its element must be in the range. And this is what we get now. This is what we can do with C++. 26. We can say static assert size of s equal to 1. If not, we display this message. But we could not do this before 26. Because before 26, the message must be an unevaluated string, such as this string, but cannot be in user-defined type. Therefore, we have to make a kind of interaction and ensure size uses here what was static assert. So what's more, the benefit is that this here, line 19 with the line 6 up to 10 are equivalent to line 22 and 23. And here's the error message, which I ignore. Template improvements. I only show you one template improvement, which is called peg indexing. This may be your favorite template improvement thing if you are a template metaprogramming friend. Have a look. First, let's concentrate on the main function. I have a function which is called first plus last. And this returns hello plus world. These are, by the way, C++ string literals. You see hello world. I can also apply to these numbers. 1 plus 10 is 11. So far it's boring. But now comes the interesting part. which is based on variadic templates. Have a look. This is first plus last. It takes an arbitrary number of arguments and returns this here. This means the 0th element of t. And this is the new stuff here. You can use an index. By the way, I could also do here something differently and just write auto. Come on. Then now it works. You see, what I had before was a so-called delayed return type, which is an 11th feature, but you can ignore it. And this is what it returns. From the values, the first one and the last one, to initialize, to create an object with type of the first type. I know this looks weird, but it's powerful. Peg indexing. You can index into a parameter peg with 0 and with the last one here, for example. Delete with reason. This means, you know what the keyword delete means? The keyword delete means you cannot invoke this function. And now what you can do is, for, let me say, readability reason, you can add a reason. I assume this will become best practice. Let me show it to you here. Here I have a function, func, and a function template func. They are overloading. And I say for double, there's an empty implementation. And for the generic case, I say delete. This means when I invoke func with a double, such as here, then only the function is invoked. When I invoke it with a floating point value, the function template is a better fit. Therefore, the compiler wants to instantiate the function template, but I set here only for double. And this is what you get in the error message also. Where is it here? Only for double. And I like this feature. Why? Because when someone reads your code and you apply the delete, it's crystal clear why you did it. Now I come to the library. There are many improvements around string and string view. For example, we have the function char conversion for converting between numbers and chars, for numbers and C strings. To chars from chars. But they are inconvenient. When you make a conversion, you have to check the error code to see if this failed or not. This is not very comfortable. With 26, you can just say if, because now it's overloaded, it supports the conversion to bool. What we also can do is interfacing string streams with string view. I'm not sure if you know what this is here. S1. S1 is a string view literal. And you can use it to initialize a string stream. This is essentially the new stuff you can do. You can also now concatenate strings in string views. Have a look. Prefix is a string view. Get string returns, of course, in string. Now to something ugly. When you want to display numbers, for example, in the UK localization, you can do it this way. When you use I/O streams, they are displayed right. You see, a point becomes a comma. But this does not work for toString. toString fails, you see. A point stays a point. And therefore, we have new overloads for arithmetic. You can use std format with a local. And now it's displayed with a comma. Here with a comma. Sorry for the big amount of text here, but I think all the points are necessary to explain. We have an in-place vector in C++26. It's dynamically resizable vector with compile time fixed capacity. It has contiguous embedded storage in which the objects are stored, and is a drop-in replacement for std vector. This means when you have a std vector, you can easily replace it with a std in-place vector. So far, I can approve it because there's no implementation available. So your question may be, when should I use a vector? When should I use an in-place vector? Here's the answer from the proposal. You should use an in-place vector when memory allocation is not possible, or is too expensive regarding performance. Also, when you have to allocate objects in static memory segments. And this is a little bit sophisticated. An array can only have elements which have a default constructor. So when the elements have no default constructor, you can use instead of a std array, a std in place vector. You want to have the possibility that it is dynamically resizable. I talk about you want to have a dynamically resizable array with const export functions. Within const export functions. Instead of that, you can use an in-place vector. And finally, when the storage location is required to be in the vector itself. For example, for supporting the C function memcopy. This was in-place vector. We have std format, of course. But std format has a few limitations. For example, it can only display void, const void, or the std null pointers. But you cannot display an int pointer. You first have to cast it. But this changes with C++26. Now you can also display an int pointer. When you use print line without any argument, you will get a line break. There are also a few ranges improvements. We get new functions, generate random, concat view, and the generate random function needs a generator G in a distribution D to create random numbers. And this is equivalent to the following for loop. Of course, more becomes const export. For example, stable sort, stable partition, in-place merge are now const export. The same holds true for the ranges pondos. Std ranges stable sort, std ranges stable partition, std ranges in-place merge are also const export in 26. Meaning they can run at compile time. We also get linear algebra support. You have to include the setter, and then you have an interface based on BLAS. BLAS stands for Basic Linear Algebra Subprograms. And what you can do essentially is you can do vector addition, scalar multiplication, linear combinations, matrix multiplication. And BLAS is the de facto standard for linear algebra libraries. This is a little bit more complicated. With C++23, we got an MD span. MD span stands for a multidimensional view on a contiguous memory area. And with 26, we get a sub-MD span, meaning you can create subviews on this span. Empty span, I mentioned it. It's not an owner. Empty span is a kind of a view on an existing contiguous memory area, and you can decide what kind of view you want to have. Let me show you these examples here. One way to create a span, once more, this is an empty span from 23, is to have a pointer and the number of elements. And this is an empty span. It starts here and has such amount of elements. And now I use this span from here, empty span, to create subspans. This is the subspan only consisting of one element, of the first element. Its rank is 0, and both elements are the same. Empty span sub1 is the same such as, sub empty span is the same such as the span here. But I can also create a different subspan. Here, the tuple 1 to 4. Now the rank is 1 because it's linear. And this is what is provided. Sub 2, 0 is equal to A1. Extend stands for the number of elements in one dimension. So the 0th dimension has 3 elements. You see 3, 1 to 4. You see also here, the 1 is included, the 4 is excluded. Now it becomes a little bit more sophisticated. I have a striated slice. This means the elements from 1 to 7 in 2 steps. So stepwise. And the same as before, it's one-dimensional, and the extent here is 4. But you can also have the full extent. This means essentially both are the same. So what's more, because it's maybe a little bit irritating. Empty span is from C++ 23, and sub-empty span is 26. This is also nice. We get debugging support. We have the functions stud breakpoint if debugging, and stud is debugger present. Stud breakpoint, of course, pauses the running program when called and passes the control to the debugger. Stud breakpoint if debugging calls stud breakpoint if debugger present returns true. A debugger present returns true if there's a debugger available. So this is the debugging support. This was essentially all the library. Because I mentioned it, I cannot try it out. And now I talk about one concurrency feature. Stud execution. but it's a big one. And it's also a challenging one. Should execution. What is it? A standard C++ framework for managing asynchronous execution on generic execution resources. Okay. Let me put it differently. This was formerly called executors, or also senders receivers. We have already a reference implementation. I will show you examples using this reference implementation. But this reference implementation is based on the revision 8 of the proposal. At currently we have 10. It has 3 main abstractions: scheduler, senders, receivers, and a set of customizable asynchronous algorithms. Now I show you one program, because there will appear a few warnings, but the reason is only that this example from GitHub is based on older versions of. Now we have it, older versions. So ignore the error messages or warnings. I will make it a little bit bigger. This is terribly small. Okay, this is the result. 1. Let me make this also a little bit bigger. 0, 1, 4. But let's see what the program is doing. This is way more interesting. First of all, I declare a thread pool of 8 threads. Then I got back a scheduler from this pool. And now comes the interesting stuff. First of all, this is not so interesting. There's a lambda function, which takes an I and returns I times I. Just remember this. But now comes the interesting stuff. It's still too small here. Now I have it. Now I schedule 3 work packages on the scheduler. This is the thread pool scheduler. First, it puts the 0 in this workflow and then applies func to it. And you know func transforms I in I times I. And then this stuff is done when all of these 3 jobs are done. So I have 3 jobs and I combine them. And here I wait. Here I wait on the result. And this is synchronous. This means, can put differently, this line's combined here in workflow or generated workflow. This workflow will only start when I say sync wait. I get back all three values, and as you see it here, this workflow gives me back a value. And the values we have are 0, 1, and 4. So I map a job on a scheduler, and I build a continuation. It looks pretty nice. This was the theoretical part. To the practical part. Let me go to and give you a little more theory. Sorry, here's another example. This is my thread pool. This thread pool can only be scheduled. Here starts my workflow, because sender is a so-called, a sender describes work. Then I say after begin, the next guy should run. You see, then. And then afterwards, after high, this lambda should run. And then I wait, say sync wait. I have to say it once more explicitly. Here, nothing is happening. You just combine a workflow. In this call here, so this is asynchronously. But this call here is synchronously. Here you trigger, let me say the pipeline, and you wait for the result, which is in this case the value. And the result will be 13 plus 42, 55. Let me add a little bit more theory. We have an execution resource. This could be a GPU. This could be a thread pool. This could be one thread. This represents the place of execution. It has no representation in the source code. Then we have a scheduler, which is the handle to this execution resource. The scheduler only supports one function, which means schedule. And now the job will be scheduled. This call returns a sender that will be complete on the execution resource. You see it here, thread pool, scheduler, and now I can only say schedule. And execution sender, this is where the workflow starts. Execution sender is a concept. I mentioned we have three key components: scheduler, sender, receiver. This was too much. Then we have the sender. You see, we have a senders and consumer. These are sender factories, meaning they create a sender. This can be scheduled, which we saw before, just here or just error, just stopped. Because this model can transfer has three channels: the value channel, the error channel, and the stopped channel. And then we have a lot of sender adapters, which allow me to adapt what I got from here. For example, you can continue on a GPU. You can, for example, build a continuation. You can start it on a special execution resource. You can split it. And what I also showed you, there's a when all. Already showed you. And here, this is the sender stuff, which you use to combine your workflow. And the consumer triggers its execution. And the consumer, of course, can return either value or an error or stopped. Once more, the sender describes work. It stands just for something to execute. And the receiver, in the slide before, it was called consumer, stops the workflow. Here I have my scheduler, my thread pool. I start the work here. I continue with this work, which reads a file. And here I wait. And nothing happens before sync wait is called. Okay. This was 26. At least what is in the draft standard. Of course, there will be some changes in the next 1-2 years. But it's highly probable that we see all what I showed you today.
Thank you for the great presentation. That was really a nice overview of what C++ 26 consists of right now. Thank you for your time.
Okay. Sounds good.